so I had a question about the final projects, right? So for the data structures, your weekly, the assignments, they will serve as combined as the final project. So you don't have to worry about the final project in the data structures, right? So, but algorithms, they will have a final project, right? So probably I'll try to do it Thursday in 2 days, or maybe next Tuesday we'll have a final project assignment. It will involve graph algorithms, obviously, right? To some extent, maybe something else extra, right? And it will be a possibility of group project, so maybe 1, 2, 3 persons can do it, right? So, okay. So now again, so if I understand correctly, or lecture-wise, we're going to have obviously lectures next week. So is the 3rd of December, I'm hearing, right? Last lecture, actual lecture. Yeah. To me?
Yeah.
Something like that, right? All right.
Also the 5th, like it's the whole week.
It's a whole week actually then. So, but we'll see again. So maybe we'll like do some catch up or something on the 5th. We'll figure out some.
Consultation.
Yeah, consultation week. Yeah, basically. That works. Okay. Now, let's go back to our hashing. So, we saw the idea of hashing function, right? And if we have a hashing string, right, we use, I was going to check if dump gives you same as dumplings. It should not. Why shouldn't it give you? Because dumplings actually use some of the early letters were used as part of this XOR function, exclusive OR. So let's do this. Here, dump, step, right?
You can also press play.
Yeah, I know, I can press play because I'll be lazy, but I want to see what's happening actually, right? But, yeah, we didn't get any, so yeah, it should give you a different value. I think 4, yeah, so there's no collision, right? So, idea is even dumplings are tasty. Let's try this one. Dumplings are tasty. Oh, I can't even do it. There's a limit actually, apparently this. No, that's it. Dumpling. Okay, let's try dumpling, right? So again, so little do no hands, right? Look, no hands, right? So idea is that we actually the S does S make a difference basically, right? It should be using this XOR function. The S initial X should be somewhere, right? Should make a difference. And let's see if this is the case. Nope, does not in this particular case. So it looks like it's still same. So this is a pretty bad thing actually, I would say. Because why? Because if you know about this type of that's using this type of hashing function, it's very easy to generate hash collisions. You just feed all these dumplings, right? Variation of dumpling, something, right? Dumpling, barbutas, right? And dumplinga, right? So, and you end up with a huge linked list collision table. So not cool, right? So again, there's another thing. Okay, with this open hashing, it seems to be, it's very less used than the other approach. So what's the problem with this open hashing is of course the linked list in itself, right? Because linked lists these days are sort of out of fashion, I could say, because of the cache collision of the caching locality, basically. Because meaning they tend to jump around the memory, right? These linked lists, right? They're dynamic, right? They tend around the memory, right? So it has additional performance penalty, right? Even though the basic implementation here is really easy, right? But these you don't. It's kind of unpredictable. So there is another approach. What do you think? What's the other approach called? What do you think? Yes, good guess. If you didn't look it up, closed hashing. Yes, it's called closed hashing. So what do you think? Here we sort of let, okay, anything goes. Whatever you want, as many keys you want. We have 13 boxes. Go ahead, knock yourself out, right? So if it's closed hashing, we have limited number of boxes. That's it. So we have 13 boxes. You better not try putting 14 items. You cannot put 14 items in closed hashing, right? But is that a problem? Well, not really, because the alternative approach is you can make it dynamic. You can resize the hash table if you want, right? You say maybe next time you'll do 29, for example, right? Some other next prime number, like 53. 53 is prime. 53 is prime, right? 53 is prime, yeah. Okay, right. so on, right? So you roughly double the size, but if you want to have dynamic, or you can just say, okay, sorry, hash table full. Sorry, try that again. So let's try this. Close open hashing, right? So maybe I'll make a new paint, another paint job. I want to do some drawing. My hand hurts from typing too much. So, right. So, right. So hopefully I'm not getting carpal syndrome. So, oh, this is cool. Right. So we have our closed caching, right? So what this means is I have my 13 boxes, right? And I can so 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay. Right. Okay. Now, so we have 13 boxes. So assuming we only have 13 items to put in, actually, well, it will work, right? The question is now, is 13 a good number to put in this type of hash table? Well, you have 13 items. Theoretically, it will work, but actually, it's kind of a bad idea. Because why? It's too little. It's too small. It's too small, basically, because it's going to be the way we're going to resolve collisions. It's going to be, well, it will involve going through this hash table, right? So let's see. Let's say we have some numbers, right? So we have some numbers, right? So we want to put, 5, 13, right, equals 5. Right, I can't spell. I can't, right? Okay, so this is 13. This is supposed to be 13, and this is supposed to be mod, right? I'm making things worse. Okay, right. But so, yeah. So obviously it goes here, right? So now, if we have 18, right? 18, right? Right? You agree it's 5 again, right? So, previously, what did we do? We put it in place. So here what we do is very interesting, right? We have collision, right? We have collision, right? We do, well, we find the next spot. And there, we'll see there are 3 different approaches, actually multiple approaches, but the easiest approach is basically look for the next available spot. We take the 6th place. It seems like kind of counterintuitive a little bit maybe, right? Why are we taking 6th place, right? Well, it's open, nobody's using it, why not use it, right? We know it's storing this value, right? It's storing this key 18, right? It's storing this 18, right? So, well, the bad news is, okay, so you say, okay, what's going to happen with 6, right? The order matters. So 6, mod 13, or is going to be 6, obviously, right? So we go to 6, okay, but it's taken, some number 18 is taking our place. What do? We go to the next one. We take 7, right? So, okay, and this stores 6, key 6. Yeah, key 6, key 18, and key 5, right? So, I call it K5, right? Here. All right. So, if you get like, let's say 9, 13, right, is 9, and we are happy, right? And if I do 22, right? So far so good. So, this is called, what we just did, it's called, what's the approach? We did it linearly. So it's called linear probing. We are sort of like checking. Is the next place taken? Is the next room open? Next room open? Next room open? Next room open? Okay. So, is this good? Is this actually used by most hash tables? What do you think? If I'm asking, probably the answer is no, right? Remember that's the old law of headlines. If the headline has an answer, the answer is probably no, right? In the news. So, see here too, yeah. So this is kind of, it works, but what's the issue? You can see it over here, right? The issue is that the next step is, next to it, right? So we tend to cluster. We tend to cluster together, right? So, yeah, it's simple to implement. I think I have an example actually in the material how I did it, but the probing step, right? So this is called linear probing, right? So linear probing, linear probing, right? So not, simple, right? But you might be thinking, okay, so what's the other approach? Well, you just need to figure out some way of jumping around, basically, right? Some other how much should you store in general in this type of structure? Well, about half, roughly about half. Once you start getting over half, you have problems basically. You'll have a more and more collisions, no matter how good your hashing function is, right? You'll start having lots of collisions. So usually you make it double the expected size, and once you have getting like over half, you make it, expand, or you maybe, I don't know, or if you can't expand, you just basically get slower performance, right? Because what's the worst case scenario? So how you get the worst case scenario? If you're getting all hashes, zero, right? Always remind, fixed, your hash function always gives zero, right? So if you have fixed hash function, obviously, right? So fixed hash function, bad function, bad hash function, linear performance, right? You always get, zero. It's basically, right? You get stop, and you get, jump, right? Same performance with a linked list. But the bad news is, of course, you get back to the array performance. Still, this is better than using linked lists in general, right? So, okay. So, does this make sort of sense? Sort of, more or less. Okay. Let's see. Actually, we're going to finish relatively early. Let's see. 1 second. I want to show something, but I'm not getting any news. 1 second. Let's see this in action. All right, so we have a oh, and T. That doesn't makes for bad neighbors. All right, so let me see. We'll see in visualization. Well, maybe we'll get to better probing approaches than what I showed you. Right, so open hashing, we should have somewhere closed hashing material. By the way, I mentioned Tom Scott, which like I said, who used to be a pretty prolific YouTuber. He had interviews, computer file, like 10 years ago, where he talked about hashing. Pretty good material. It's in the course materials here. When you have free time, you can watch it. It's like 10 minutes or so here. The link. Okay, but let's look close hashing visualization. All right, yeah. So close hashing, fixed size. So we have, let's do integer, right? So notice it has 3 probing. So now we saw the linear probing. So something called quadratic probing. So what the idea is, the next place where we're going to look for is going to be multiplied by the index. So what does it accomplish? It accomplishes that our linear probing, right, Control S, closed hashing, right, that we are going to jump around. We are going to jump around not like this, right, but linear, right, linear, well, maybe make it linear, right, and let's say you have the next place, so on quadratic, so basically 1, right, then you have, I believe, 1, and then you have 2 to the power, I guess you have 4, I believe, let's see, 1, let's see, 3, and then 4, 7, and then maybe something like this, quadratic. think so. Okay. And there are other approaches too. So let's explore the simple ones, the linear ones. So again, integer key, so it's easy. So I'll do number 5. Right? Easy here. Okay. But now slow it down. Pause. Right. So let's do again. We now 18. No, sorry, 20. Oh, this has 29 slots. So 34. 34, right? 34, right? 34 is going to have a collision, right? There's a collision. So where is it going to be? Where is this 34 key is going to go? In which place? We have a collision. So
25.
you think? No, we already did model. It's index 5. It's supposed to go here, but it's taken. We're doing linear probing. Where?
Linear?
Yeah.
Doesn't do 6.
Yeah, of course. Yeah, this is not trick question, but an easy question, right? So step forward 6, of course, right? All right. So let's do, well, obviously, if I do it again, let's do, so if I do 63, right? 63, play, I'll do it quickly. It's go here, right? You're not going to be surprised, right? Right. So how about 30? So 30, where is 30 going to be inserted? Yeah, exactly. Very good. Very good. Perfect. Right. So has no collision so far. Well, we had 2 collisions here, no collision here, right? We have plenty of room, right? Everything is good. Except, of course, the problem is if for some reason we get some sort of like power or something, we get this cluster of things. Like if I'm again, it's not really end of the world, of course, but it's kind of annoying because it doesn't spread out the usage. You want to usually spread out the values, right? So let's do 92, right? I can't, my math is kind of off, right? 92, collision, 8, right? So if I do 7, where is it going to be? No, sorry, 36, right? 36 mod is 7, so where is it going to go? Yeah, of course. I mean, it's easy. It's easy to see, right? And so on and so on. So yeah. So basically, any time we hit here, we just keep filling up. It's basically, we end up doing a lot of jumping over, right? So it's not so good actually, right? You want sort of like a spread it all over, right? Basically, right? So let's do quadratic probing. And this kind of a little bit harder to implement. So again, I'll do 5, right? 5. Insert. Here, no problem, same thing. And again, I'll do pause, and let's see what's going to happen next time. So, 34, right? 34. 5. Okay. Collision, and we do 1, right? Index, right? We probe. This is our first probing is 1. F of 1, this function, right? Right? Next place to check, right? This is a probing means looking for something, right? Looking for next place. And the probing is kind of not very positive word, I don't think, but it's okay. It is what it is. So this is called function of 1, right? So it gives you 1 times 1, right? Next time is going to be what? So next time we're going to look. So if this is function 1, so function of 2 is going to be quadratic. It's going to be 4. So it's probably going to be here, I think, right? Let's take a look. So 63, right? 63? Yeah, 63. Insert. We have 5. Let's take a look. Problem. Not a problem, right? So quadratic probing has some good advantages. It spreads things out. It's also pretty quick to calculate. So I think it's good middle ground, personally. Personally, I like it. If you don't, you might not don't have to like it. Right? Now let's do the third one. So I'll do 92, right? 92, insert, 5, again collision. So 1 is 1, function of 2 is 4, and function of 3 is 9, so 5 plus 9 is 14. That's where we put the next item. So if I do another collision, let's see, 121, right? 121, right? Where is it going to be placed? 21? Yeah, I think so. 21, I think, right? 5 plus 16, right? Yeah, 5 plus 16. Yeah, you got it. You got it. Very good. So let's do 121. Insert 5. Okay. Okay, you'll see this idea. So here's the advantage. So now if I want to put 6 here, right? I want to put 6. You'll see the advantage now. So 6 now will go to 7, so it'll have its own jumping around place, basically, right? So if you have similar numbers, you'll still get some clusterization, right? But it's not going to be as obvious and so as clustered. Of course, the last thing is to do another hash on top of hash. So it's like we're building a hash on top. You have another hash function. You can use whatever you want, same one, which sort of provides a more spread out, even instead of just quadratic, you have a hash function, right? So let's insert 6 first. On. It goes here, right? So if I have collision with, let's see, 35, right? So where is going to be 35? Probably here, right? 6 plus 4. 6 plus 4 is 10, right? And so on and so on and so on. Okay. So how are you guys doing on quadratic probing? You could do it yourself too, right? No problem. Yeah. Just probe function, basically implement probe function. We have like maybe 5 minutes. I'll show you double hashing, right? Yeah. Second. All right, let's try it. So, double hashing. So this means you have I plus element hash, basically. So, let's try it. Let's do 5. And let's do double hashing. Insert 5. And no problem, right? But we have a hash. So actually we're not in the 5. We are, yeah, actually here, right? So let's do 34. So if there's no conflict, it doesn't do a hashing step. So now, basically, we have a problem. And hash function is 1 minus 34 divided by mod 7, 1. And this, of course, is not as easy to see, right? You can't really predict it, like if you don't know the hash function. I mean, a good hash function is really almost like a black box, right? So here it's 1, right? But let's see next collision. I want to see the next collision. 63 on 7. Yeah, you instead of getting 4 as quadratic, you get 7 basically, and it spreads things out even nicer. And again, double hashing is, I think, most most production grade hash tables, I think, use double hashing, right? So again, there's been some heavy math behind it. The load factor of a hash table, right? 0.5 generally is bad. If you go over 0.5, right? So 40% full is okay. 70% full, it's gonna degrade the performance. It'll still work. You'll get some advantages, but you'll be getting lots of collisions, right? So there's no way around it. Again, if you have strings, the only step is that, let's say, RBS, right, is going to be the hash function, right? Insert RBS, you need to hash it first, right? And I'll do play, right? It's going to be something. I don't know what it's going to be. 5? I forget. That's about a 0 or 1. I forget now. Yeah, 27. Ah, here, because different mode here, right? All right. And now, of course, I don't know how to make a collision easily, right? So this is now, again, like as a naive attacker, right, myself, I can't make an easy collision, basically. I could make some, maybe figure out something. In this case, it's already allowing me strings. So, okay, of course, the good news for you is that pretty much most languages, I would say, unless you're doing some really esoteric language like BrainF or something, right, is going to have a hash table implementation. Use that, right? So as far as C++ goes, right, one thing I should let you know is that C++ map, right, they use called map, right, C++ reference, right. So this is the thing you should remember, that it is not, it's sorted, right. So if you need the best performance, don't use this, right. It's nice, right, but by default it's sorted. If you don't need the sorted capability, you use unsorted map, right. Where is it? Where does it say? Come on. There. Unordered map, right. This is what I think. Generally, I'm personally, I'm sure they had some data what people use by default. I mean, they both. I mean, it doesn't cost you anything extra as far as compilation speed or anything like. It's just name. It's just names, but names matter. In most languages I've used, the mapping, the hash table by default is unordered, right? Here, by default it's ordered, right? So what's the difference? O1. This is O1, right? This is O1. Basically, it doesn't mention what kind of what's underneath. Well, that's up to the language implementation, right? I don't think there is the standard does not say, okay, you have to use quadratic probing with a closed container cloning. No, it doesn't. I don't think it says anything, right? It's up to the specific language, right? So there's still research ongoing about this actually. So there's some improvements. I wanted to actually add the simple hash table implementation maybe quickly to the or data structures code, maybe, so you can see this in action. Maybe try it or yourself out if you want for fun, right? Let's do something quickly. Which one should we do? Closed or open? Probably closed, I think, is easier. Yeah, with linear probing for now. Let's do like, or maybe for that. I mean, it shouldn't really matter, right? We can change it afterwards, right? So we'll call it closed hashing. Should be quick enough. Closed hashing. Oh, come on. What happened? I can't spell it. Rename. CPP. Implement the closed hashing data structure, right? It will be unordered, right? It'll use fixed size. For collisions, we will use no. Let's use quadratic probing. Let's try it. I'm gonna, okay, that's it. Keys will be integers, right? Values will be strings. Okay, why not, right? Again, so this is not generic, obviously, right? So to do generic later, right? Okay. Now, so include IO stream. That's it. Using namespace string. Yeah, sure. We need string, right? Using namespace. So let's do it. Let's see what the AI comes up with. It's thinking. Okay, close hatching. So private, right? Stuff we don't. The user, right? Meaning you, right? You don't want to see this. It's all private. Size, keys, string values, right? So capacity, count, hash, probe, right? Notice this is a probe function. I would like to see probe. Oh, it's using hash as well. I think it's using. It's not actually quadratic. You see, this is it's not using. Oh no, that's correct. Hash key plus it's quadratic probing. So quadratic probe, right? Close hashing. New, right? Is there going to be destructor? Delete keys, delete values. Okay, super, right? So delete keys and values, right? So we save the data underneath. There's an array of strings. There's an array of keys, right? Looks like this. Values, keys, right? Because, yeah, and of course, so keys. So what's happening? You have so if you look for how it's going to work, let's see. Size, this is fine, of course. Oh, it's probably storing the number keys new in size. We'll see this. Okay, insert hash table is full. Right, keys index, key index. Yeah, looks okay. Let's see this in action. Right, so let's test. Let's test it. Let's see. Yeah, exactly. So int main. Right. Come on. All right. So 10. So we did well. 10 is a good number. No, not good. Let's do 13, of course, right? Remember, premise good for hashing tables. Yeah. All right, so 1, 2, 3. So let's not go there. Let's see. Remember, can we? Is there some? What's happening with the hash function? Can I do? Yeah, hash. Yeah, good. So key size. Yeah, very simple hash function. Ridiculously simple hash function. So I will do let's do some collisions, right? One. Let's do this here. 2. Let's do not 13, but insert 15, right? Collision. No, 5, 28. I wonder if it's going to learn what I'm trying to do. It's not 28. Okay, it knows that much, right? Let's do one. It's going to do 41. Nope, it still wants to do 5. Okay, right. Search for search for 5 doesn't exist. Search for 28, right? Of course. And let's see if we can finish this. Right, 1 minute. And remove. Right, 5, 28. And let's see this. Right. Okay. Let's see this in action. C++ or G++, close hashing. Come on. It's not there? Oh, okay. Out C hash. Yeah, it compiled. I don't know how. Yeah, so it works. Search for 5. It didn't find 5. Well, because I didn't have it. Right, good. Right? So it works. There's no crashes. That's good. Right? I'm not, meaning if you search for something not existing, you still find it. That's good. So something to look at again. So you could simply, this part here, right? Where is it? Where's my probing function? Come on. This part here, right? So this is here. You replace I times I with a function call to probing, call to some probing, some other probing functions such as secondary hash function, for example. Yeah. So this, of course, this is quadratic. You can if it's I, it's will be linear, right? So, okay. So are we good now? Good. Super. So you got the basics again. Use the built-in ones, but this is already getting you a good start. So see you on Thursday.